Hello, can everybody hear me? Hello. So, today I will try to share with you a little bit of the little I have learned over the last 3 decades working at the frontier of science and technology at CERN in Geneva, Switzerland. Thank you for giving me this opportunity, and thank you for having the patience of listening to me over the web. And it's not an easy task for everyone, given the world situation, given the very challenging situation at the moment, and I wish everybody all the best. So, why exactly are we here? We are here in search of answers. And the answers we would like are to many questions that we have had over the years as we have grown up and as we have. Just a moment, I'm not able to share my screen. This is very difficult. Why can't I share my screen? It's a bit of an issue. Let me try this. Hello? 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 Which application window? Yes, so I did application window, but I'm not seeing the key. Yeah, it's open. Yeah, it's open. I am seeing it there. Because right now it was working with you when we tried it out, right? Yeah. Okay, now what is the problem? Application window. Just let me try again. Is it working now? Let me see again. Share application window. Yeah, it's showing. It's not showing. It's not showing on the Jitsi. It's not showing on the Jitsi. That's the. Arey Baba, it's open. I will open again. Okay, I will just open again. Once again, I will open. So now it's open. Once again, I reopened it again, and let me go back again and see if that is working now. Application window. Yeah, I think I found it. Okay, there was some problem going on. Can you check if I can see? You can see my screen. Okay. Very sorry for this technical hitch. Despite all the technology, it's not easy for us sometimes to get over these kind of issues. So thank you for your patience. So yes, we are here to answer questions, and most of the questions are going along with us ever since we were children. Where did we come from? What is the world made of? And what holds the world together? And then we have, of course, the title of today's seminar is The Cosmic Dance at the Frontiers of Science and Technology. So as you see in this picture, you see Dr. Kakodkar here, you see Dr. Robert Emmer here, the Director General of CERN, and our ambassador here, who had gifted this very beautiful Nataraj, the cosmic dance symbol of India, to CERN, CERN, the Laboratory of Particle Physics here in Geneva, Switzerland. And what are we doing here in Switzerland? We are looking at trying to recreate in a very minuscule, very tiny, very controlled laboratory conditions, the Big Bang. Most of you have heard about the Big Bang. You have heard that the universe or the multiverse has been expanding, and it was very, very hot, million times that from the inside of the sun when the whole thing started at the time of the Big Bang. And a little time after the Big Bang, little time meaning just a few seconds, there was an inflationary phase when this expansion started. And of course, there were tiny particles that formed. It was like the birth of our universe. What we study is to understand how this whole thing happened when there were no other states of matter available. There was no gas, liquid, solid, and things that we understand physically today. So, what was there just immediately after the time of the Big Bang? When we will answer these questions, we might be able to get a recipe on how the universe came about. So, in another picture here, you see that the temperature is given on this scale on the bottom, and the time scale is given on the top over there. So starting from a soup of particles or a soup of, we do not know what was at the time immediately after the Big Bang, small particles formed, and after these small particles formed elements from molecules, atoms, and so on, and the elements as we know them today. And over 1,000 million years, thousands of million years, in fact, 15,000 to be precise, we came to the point where we humans are right there and reflecting on these issues that I was just speaking about. And I am a minuscule person in this whole game. There are large collaborations all over the planet, large theories that have been put forward, and of course, it encompasses the scientific community as a whole. You may be familiar with the structure of matter as you see here in the periodic table. So once we knew the atoms, elements, we nicely, Mendeleev put them together in the periodic table. It makes a lot of sense. We understand how the elements behave, how they combine with each other, and what are the chemical forces in between molecules of different types of elements, and how they create compounds. So that literally tells us how the universe was made, starting from a tiny a soup from the Big Bang, just after the Big Bang. So moving further, once we understood the atoms, of course, the quest goes on. You know, scientists are like children. They want to play. They want to break it further and try to understand what's inside the atom. And of course, most of you have learned in high school that the atom is consisting of a nucleus, consisting of protons and neutrons, which probably at the time when we studied, we didn't exactly understand, but we learned that there were quarks that actually form the protons and neutrons. And then, of course, there was the electron. These are the smallest building blocks of matter when you put them all together. So how did we come to this conclusion? There were scientists who have been busy doing many experiments with going high in high altitudes, looking for cosmic rays, looking for the echoes, the reverberation of the Big Bang that still would exist and has been proven. Then there are pictures that have been taken at high altitudes in balloons, and India has been very involved in those kind of experiments in the 50s, in the 60s, and has been pioneering, in fact, in many of those results. So we in India have a large number of scientists who have given us very big shoulders on which we can stand and claim that, you know, we know something. So here is not an exhaustive list of the scientists from India, but you see some of the names you recognize and you immediately know how big their contribution is. I will just call out the name of Dr. Satyendranath Bose. You know that boson, the name boson, the family of particles that obey the laws that were created by Bose and by Einstein, are called bosons. And of course, there are many other contributions that are given to science, given to physics by India, and it will be impossible to go through all these contributions without it's impossible to do justice to this. On the right you see balloons going up, and this is in Hyderabad, by the way, and this experiment was conducted by none other than the pioneers, Dr. Bhabha, and the others in Tata Institute and in Hyderabad. And I will just stop here for the history part of it. Now let's move to the future, and the future is an unknown. We have no idea what is it out there. Is there just one universe? Are there other universes? What happened to the antimatter? Just the fact that we are here, just the fact that we are here will tell us that where is my antimatter twin? I think in high school we learned that there is conservation, something called conservation. So if there is a negative quantity, there must be an equal and opposite positive quantity so that they can balance the charge or the forces or the conservation of momentum or the conservation of energy and so on. So similarly, at the time of the Big Bang, if, let us say, the stardust that was formed or the soup that was formed contained matter particles, which we are talking about, and these matter particles are those protons inside our bodies. All our bodies were together at that point of time in that cosmic soup. Where is the antimatter? There must have been antimatter also produced at the same time, an equal amount. But if it was equal, it would have annihilated and we should not be there. But we are here. So there is this mystery. Where has all the antimatter gone? In addition, if you look for, just a second, let me share my screen. I hope it's working properly. Yes. So if I go to look for other observations that scientists have made, and these observations come in way of something called dark matter and dark energy, which is nothing so special. Do not be bewildered by these terms, because when scientists do not understand something, they call it dark. And dark matter and dark energy is there to explain to us why the visible universe is so small as compared to so much that should be there, in fact, right? Clues that there should be something out there, and that's for the moment uh, denoted by dark matter and dark energy as well. So we are going to look for for answers to these kind of questions. We will also try to understand what is it, this primordial plasma, the soup at the time of the Big Bang we were speaking about. What is it made of? Is it things we know? We certainly know that it was not liquid, gas, or solids like we know around us, but we know that it was made out of very, very tiny elementary particles, some of which we know. So how can we do this? How can we look forward to understanding these answers, these questions? We must go back in time. And to go back in time, we must create matter. How much fun that sounds, but it's very, very, very difficult. So when we have studied all the cosmic rays, the studies of balloon exposures and so on, just like the periodic table, I would just like to submit to your attention that there is something called the standard model. The standard model of physics, which tells us that the smallest particles belong in three families. The first family, the second family, and the third family, like you see here. And these are the quarks, of which the up and the down quark are the ones that are the most prevalent in matter, and the others we have observed them, but they are not stable. They are heavier ones, heavier cousins of the up and down. And similarly, the electron also has cousins. There is the muon, tauon, and so on. So without going into too much detail, let us understand that we can put together a particle, a table called the standard model, where the particles that we have observed, they explain to us the nature of the universe. They explain to us why atoms can form because of the nuclear force inside the nucleus between the protons, how the electromagnetic force manifests itself, how the nuclear force manifests itself as well. And we know every day we have the sunlight that comes to us from the sun, and we know that the photons from the sun are responsible for the electromagnetic force. So we have now understood that there are particles and there are forces. So the forces are mediated by these kind of bosons called gauge bosons. Let's not go into the jargon. Let's just imagine that forces need bosons to operate. Some of them are very obvious, and some of them we have to look for. So in many experiments in the past, these force bosons have been found, and some of them have been found at CERN. Some of them are still have been hunted over the last decade, because you can imagine that experiments are not easy. Experiments are very, very difficult, but the standard model gives us an understanding of the fundamental particles and the fundamental forces of nature. All this together, whatever I have been speaking about, tells us about the four forces, the fundamental particles, the four forces being electromagnetism, nuclear force, weak nuclear force, and gravity. And together they make the sun shine, and they make our days bright, and they give us the night and day, in fact, because of all these forces. So now let's get into action, and we would like now to create particles. How can we create particles? We first go to Google and we try to understand how can we create particles. And of course, Google will tell you, you need an accelerator. What is an accelerator? Oh God, in Hindi it's called twarak. So we do know the equation, the one equation called E is equal to mc squared. It means that if there is enough energy, we will be able to create matter. What a fantastic thought. So if we have accelerators, and just like when we played when we were kids, like throwing stones and smashing stones into each other, or breaking up old equipment to understand what's inside, we physicists have been using protons, in this particular case, to accelerate the protons with cavities and so on, with a special equipment. And then we are able to reproduce the conditions that might have existed at the beginning of the universe, right after the Big Bang. So this has been a very exciting journey, and we have to understand how to do this. Everything has to be controlled in terms of safety, in terms of awareness of how we do it and explain to the public, because generally the public starts imagining, oh God, if there is a Big Bang close to me in a laboratory, is it dangerous for me? Will it create radiation? But no, certainly not, because the amount of energy that is needed for recreating the Big Bang at a very, very minuscule stage inside the laboratory is equivalent to connecting 10 to the power 12 mosquitoes, but in the space of the top of a needle. So let me explain to you. Imagine that you have protons whizzing around in one direction in bunches, and protons whizzing around in the other direction also in bunches, and then they are made to collide at a certain point. And look what can happen. So imagine you have mosquitoes. These mosquitoes have energies which are like 10 to the power 12 batteries, that kind of energy. And then when they collide, we find that from this energy, because of the equation that we just said, E is equal to mc squared, we are able to produce known particles. We are able to make cats and dogs and horses and pigs and fish and so on, and turtles as well. But we could find things that we do not know. We could find things that we know that they existed, like the dinosaurs, but they do not exist today, right? But we know that the dinosaurs existed because we have seen signatures, we have seen fossils, we have seen the remains, and we made theories that they have become extinct, but they existed. So in a similar fashion, we have this large accelerator at CERN in Geneva, Switzerland, where if you look here, I'm going to just play this if it works. Yes, so you can see that we have protons going around underground, and they collide at one point. They are made to collide where they recreate the conditions of the Big Bang. Just to place your references, you can see here the aerial view, and there is an accelerator. The airport of Geneva is right here. And the scale of the experiment, you can imagine this circle that is representing an underground tunnel is 27 kilometers in circumference. The scale here you see just shows you the dimensions as such, you know. When you want to look into galaxies, or you want to look into the universe, you need telescopes like the Hubble telescope. There are experiments on the International Space Station that are also conducting inquiry into several of these kind of questions that we just said. And at CERN, we have this accelerator called the Large Hadron Collider. It is a super microscope which is reproducing the conditions at the time of the Big Bang.
It's 2 o'clock.
Okay, so now, how many of you did know already that there exists this laboratory at CERN? I suppose many of you would know about it, right? But then we need to raise awareness of science to our general children, to students, to kids who are interested in science, simply because there is such a big opportunity. And the opportunity is that in India particularly, I am sure many people know about the Bollywood craze that we have in all the shooting locations in Switzerland, which are shown every time when you watch a movie, or at least when you're exposed to looking at these things. So under all these beautiful meadows where the cows have no idea that underground protons are whizzing around, crossing the border between France and Switzerland and recreating the cosmic dance. So we absolutely have to reconcile to the fact that creation in terms of the dance of Shiva is what we have known and grown up with. It's the cosmic energy. It's just an expression of dance, and this expression is also being given to us that, for example, every proton, in fact, मैं हिंदी में पढ़ती हूँ इसको, हर प्रोटॉन कभी कभी सृजन और विनाश के नृत्य की इस प्रक्रिया से गुजरता है. यानी कि जब ये त्वरक चलता है, इसके प्रोटॉन्स जाते हैं 27 किलोमीटर चक्कर लगाते हैं. उसके बाद जब वो एक साथ टकराते हैं और एक तरह का छोटा सा माइन्यूट सा विस्फोट होता है, तो ये नृत्य दोबारा हमें दिखता है. लेकिन हम इसको विनाश नहीं समझ सकते हैं. इसको हम ये समझते हैं कि हम इससे क्या सीख सकते हैं. So here we are on the instructions of how the matter was formed, and the position where you see these arrows are marked is where the Large Hadron Collider, as it is called, will lead us to answering the questions about the basic open questions we studied before, which are, of course, that are the fundamental constituents of matter, the fundamental constituents of matter that we know now, or are there still smaller particles, or are there dark matter candidates, are there other theories which we do not know? And for all that, we have to go underground. As I mentioned to you, that there is the surface here is crossing two countries, Geneva on the right hand side over here and France on the left side over here. And in this scheme, you see, if you go underground, there are four shafts, and there the experiments are located. And in this program of research, we started building all this 25 years ago. And from 25 years ago, when we started to build the accelerator, and concurrently the detectors are like mobile cameras. You all use mobile cameras, right? And you take many pictures every day. But we have been taking pictures 40 million times per second inside the accelerator, looking for these collisions and trying to understand and make sense of uh, understanding what are the missing part of the standard model. Where I missed out one point, very important point, was that for the interaction between the quarks, and you remember that there was a boson, the boson that actually allows us to have these interactions. Similarly, why and how at all particles got mass, right? So when there was this soup of particles at the time of the Big Bang, there was no mass in the particles. How did mass come about? And this was given to us in terms of a theory. So let's try to look at how this was proposed. So in 1964, of course, the questions were open from a very long time, being discussed by many, many physicists and scientists. But in 1964, six physicists, they proposed an explanation, a very interesting explanation by means of one mathematical equation. And that equation produces, by means of this equation, produces mass to particles by interacting with the Higgs boson. Of course, the name Higgs came later on, which was attributed to Professor Peter Higgs, but the name boson was already there, as I mentioned, for the family of the particles. So this Higgs boson completes the standard model, as we said before. So we wanted to reflect on how to find this Higgs boson in our accelerator, in the collisions that we see. And on this cup, you see, just like you know one equation called E is equal to mc squared. Do not get scared by this equation on the cup. It actually encompasses the whole universe, how you create particles and how you give mass to them and how they interact with each other and so on. So fantastic. Now let's go on the Higgs hunt. So Higgs is not produced every day. If it were, we would have already found it, right? So we need to have lots and lots and lots and lots of data to be able to find one particle. It's like finding that one grain of gold on the beaches of Goa, okay? So it's very, very difficult. Nevertheless, it was found, and after 2 years of data taking, it was found at the Large Hadron Collider by two of the experiments. So how did we go about for the search? The search is very complex, as you can imagine. It's not an experiment in a small laboratory where you can sit together and chat with your colleagues and you say, okay, this is my theory and let me test it quickly on a bench and I can come with answers. It's not really like that. So here we need the powerful accelerator, which I mentioned to you. The detectors are our mobile cameras that take pictures. Of course, we need a lot of computing power, because how will we analyze? Every time we take the sand in the bucket, we have to check with different algorithms whether there is my gold grain or not. So we need very, very fancy algorithms to trigger and keep only good data and throw away the data that we cannot use. And all that is done by collaborative science on a worldwide scale, with thousands of scientists, engineers, technicians, and support staff who build and operate these machines. So this is one picture inside the tunnel, and you see that what I just mentioned to you, these are not mosquitoes anymore. They are protons, and they are going to collide with each other. So not only the Higgs boson, but we will completely look at other things. Maybe we find some unknown unknowns. We have no idea. So this is an extraordinary machine, and the machine can operate only with superconducting magnets. And of course, when we do experiments of this scale, it is incredible that we are able, and all of science, in fact, all of the spin off that we have from science, we are injecting technology into society. When you go to the hospital, when I go to the hospital with a broken hand, I say, oh, मुझे एक्सरे करना है. अब वो एक्सरे आया कहाँ से, आप सोचिए. X-ray has been now old technology. Now we are entering into a completely different era. The kind of technologies that you encounter every single day has been, in one way or the other, a spin-off of investigation in science. Every dollar that is spent in science goes back to the society multiplied by a factor of 4. And this is why we need to continue this inquiry, continue the research, and that is what also gives us the big encouragement on how we are able to continue giving and participating in this high-end research. So remember, we have the temperatures very, very high, much hotter than a billion times than in the center of the sun. Empty vacuum only, because how do you collide protons? If you have air in the beam pipes, you will lose your protons. So the vacuum is better than that on the moon. The cryogenics is incredible. And of course, the magnets themselves are one of a kind, 18 meters long each, and they give very, very strong magnetic fields. And let us look at our mobile cameras with which we take pictures. These are the two very big experiments. One is called the Atlas experiment, and the other is called the CMS experiment. Let me not go into the details, but take it from me that each of the layers of these cylindrical onions and each of the cells of these cylindrical onions represents a mobile camera. So we are taking 40 million times a second pictures with each of these cells, and the number of cells is more than 70 million. So this is the only way we are able to reproduce the Higgs boson. I was fortunate to work in this experiment. It's been 20 years now, and this is what you see here is part of the experiment, not even the complete picture, but you see some people working here, and day and night they have been working. Eventually, of course, the results have been spectacular. So these are some pictures where these are the engineering marvels that sit inside the experiments. You see just some pictures here. Here, these are some kind of detectors that personally I am involved with, and those are some challenges which the data has to see, because we need to have the fastest PCs, 100,000 of today's fastest PCs. And at CERN, we have only 20% of the capacity. So, sorry, am I still showing? I hope I am. So we have now something called grid computing, which means that we are sharing the task with all the tiers in the world. And the tier 1 site, tier 0 is at CERN, and then the tier 1 sites are all around in the world. In India also, we have a couple of tier 2 sites that participate in this work. The data challenge is incredible. The CPU scaling is now coming to an end. So now there will be GPU scaling, which is coming, because up to now, for myself, it was, when we started working, we could think of kilobytes, then megabytes came, gigabytes came, petabytes came. Now we have 100 petabytes of data to look at in 1 year. Now we need to prepare for the future. And there we are preparing for exabytes of data. So all that preparation in the end yields very. And we also use artificial neural networks. We use machine learning, and all of the trade that you can imagine. Then we capture the decay of a Higgs boson, which then, this in the center you see a Higgs, and you see four muons going back to back, two muons back to back, and that is a gold plated signature of the Higgs boson. It's like the dinosaur fossils that we have found. And then it's not the only way the Higgs can decay into four muons. It can decay into other particles also. So those studies have been very seriously done. And it is an incredible feeling when the Higgs was actually discovered. These pictures may be complicated to understand, but you can imagine that these little blips here are the blips that has won the Nobel Prize for CERN and for all the scientists that have announced on the 4th of July in 2012, the discovery of the Higgs boson. So that was an incredible participation, incredible collaboration. And of course, in India also, we have very big collaborations working in part of all the work that I have described. So clearly, big seminars where all over the world people are looking, and when this was being live declared, and I went at 5 a.m. in the morning to find a place in this auditorium, but I did not find place. I was still in the queue about 100 meters away. But then in December, the Nobel Prize was given, and of course it was a very big moment. So what do we do next? So the Higgs is like a newborn baby. There are many, many questions it will answer in the future. So the studies go on, of course. So now, this I have already mentioned about dark matter and supersymmetric particles. This is just the other challenges that are coming up in front of us. So now let me move to another very clear topic to me, the innovation part of particle physics. So what we do is extremely exciting, challenging, because 20 years ago we had no idea whether we will have the technology to actually build the accelerator, to build these detectors. So we have been working hand in hand with industry, and interfacing fundamental science with society is part of the mandate of every scientist and every science student. Today, in these challenging times, I think every scientist is scratching their heads to understand, how can I help? So at CERN, we have three groups of tasks that we do: the accelerating particle beams, then we are detecting the particles, and of course, we are analyzing all the data. So medical application is a very important, many applications are there. And let me take an example of hadron therapy. Hadron therapy is using accelerators to treat cancer tumors. So if you look at this picture here, where an X-ray is shown to a patient and the whole of his head is illuminated in order to cure the tumor, unfortunately, a lot of damage happens in the tissues, in the healthy tissues around the tumor. When we use particles, protons, or light ions, which can be accelerated and tuned to the right energies, we will be able to create a digital scalpel. And this is not that we will be able to create, these technologies are already operational. And there are several facilities all over the world, and 100,000, 1 lakh patients have been treated worldwide in such facilities. Similarly, the scanners in the hospitals use most of the techniques that we have developed, simply because we have to look for collisions. They are like cameras. So those cameras can then be used in hospitals. The technologies can then be used in hospitals, and so on. I mean, I will not go through all that, but might want to mention that The www, the three words that you know very well, and many of us are in love with it, were actually innovated and invented at CERN by Sir Tim Berners-Lee, who was a 22-year-old student when he was working at CERN as a student. Yes, so he went to his supervisor and said, "Look, I think I have an idea of how we can use HTTP for communicating between remote computers." And his boss wrote on the paper, "Vague but exciting." And just look at the world today, where we cannot literally live, not only live, but we are serving the world, serving societies, and saving lives using www. And of course, there are many applications which I do not have to tell you all. All of you are very, very familiar by how we can use distributed computing, how we can use for the web or the grid for education and training. You know, when I grew up, I learned mathematics by writing very long equations. Sometimes they used to go from one page to the next. Some of my college colleagues would remember that we have to turn the page to look at the second part of the equation, and even then many a time we were unable to fathom where am I going to apply this equation. But if you see pistons in action, movement in action, the relationship between space and time in action, the education today is become democratic. There are no borders, and any student who wishes to study, who has a repertoire of knowledge in front of him using the World Wide Web. All right, another big thing that I have learned, and another big learning all the years that I have been at CERN, is about collaboration. These are some pictures of collaborations at CERN. We are thousands of physicists in one collaboration, and the power of a collaboration is incredible, because there is competition, of course. Healthy competition is important, but when we come together as a collaboration with a single goal, then 1 plus 1 becomes 11. And that I had to learn, and I think it's a very important lesson also for the future, for our scientists, for our kids who want to take up science in the future. And that's how they are successful, because there are clear definitions and on who will do what and so on. And just imagine, it was impossible for the theory that was proposed in 1964 to have actually yielded the Higgs boson in 2012 if we were not working together. So large collaborations are very, very successful. And of course, by the way, the data is completely free and available everywhere. So if anybody is interested, you just have to type open data LHC and you are able to be engaged. So it's a very, very open policy as well. For the future, so this is fantastic. We have a machine that is going on. It is being upgraded. The energies will be increased. The luminosity, so we speak, which means number of collisions, will also be increased. And you have also noted that it took nearly 30 years to come to today. So the next collider that is going to be built has to start today to be operational in 2040 or later, right? So those plans are being drawn out at the moment, and that is going to be called a future circular collider. The circumference will be of the order of 100 kilometers. So indeed, all this is very mind-boggling and very confusing and very unclear, very disorienting, but then there is hope. The hope is that we can participate. Every person can participate. Every student can participate, and there are things to be done on a piece of paper. There are things to be done on a computer. There are simulations to be done. We can work in laboratories. In India, we have many, many, many laboratories where any interested person or student can go and take part. Then there are virtual visits at CERN where students can participate and speak with experts and talk to them, ask their questions. And we have had many, many exhilarating moments with students at CERN who have been with us for as short time as a week and as long time as few months, up to a year, and so on. There are many programs at CERN that go on. So these are examples that Not everybody can come to CERN. It has been a privilege for me to work, but this is why I reach out as much as possible to school students, to college students, to colleagues in the country, so that we are able to set up other programs by means of which we are able to share what we do at CERN. And it is a completely democratic science, and we want to have as many people as possible to work together. Let me just tell you an anecdote about antimatter. So antimatter we can create, but it is very, very expensive. So somebody out there who is an economist or a finance whiz, he might think that let's think about an antimatter economy, because if we have even 1 gram of antimatter, it will solve the problem of humanity for hundreds of years, or if not thousands of years, in terms of energy and so on. The only thing is that it will cost you $100 trillion. So at the moment we do not know, but I do know that in IISc Bangalore there are scientists who are working in this field. And when I tried to have a very small project for some students based on the cooling capacity, or the project whereby we can trap antimatter, was being discussed at CERN. It was such a proud moment for me when they said that the best technology exists in IISc Bangalore. So today we are all open, we are all unleashing our potential in the best way possible. So for me, I think working in particle physics has been a very interesting, exciting, and very empowering journey. And I can report that if I can do particle physics, anybody can do this. I grew up in India, studied in India, and so on. In addition, once you can do particle physics, you can do anything, because the projects are so long. The projects have a period from where you start prototyping, learning, and so on. You go through the data taking phases, the analysis phases, and then of course you saw those big objects that were being lowered down in the cavern. Each one of them weighs something like 2000 tons. 2000 tons is like, I don't know, 100 elephants, or maybe you want to tell me. So, how do we handle them? There are no cranes that are built to lower these objects. So, on the spot, solutions have to be found, and so on. So, I will not go into too much detail, but you can probably already infer that applications in terms of financial management, risk management, medical imaging, and safety, security, radiation management, and of course, project management, detectors for astrophysics and cosmology, so on. So they just demonstrate the multidisciplinarity of particle physics. So, yes, we I continue to propagate and invite you to join the mission of the dance at the cosmic frontier, where we push back the frontiers of knowledge. We develop new technologies for accelerators and detectors and information technologies. We train the scientists and engineers of tomorrow, and we unite people from different countries and cultures. It is an amazing, enriching experience to work with people from different places and to learn about our own limitations of mindsets and limitations of how immediately we infer things. And this is the biggest lesson that I have learned. So I would like to conclude at this moment. The woods are lovely, dark and deep, but I have promises to keep, and miles to go before I sleep, and miles to go before I sleep. So here I will be open to questions, and you can please go ahead with your questions. I cannot hear anybody. Can you still hear me? Hello? Can you still hear me? Hello, can I hear? I do not see.
No, you can see the live chat only, no voice call.
Okay, so I'm unable to see.
Just scroll there, that live chat, YouTube and live chat.
Oh, I have to go up. Okay, good. Thank you. Okay, so I see some questions here. Let me just see. Thank you very much for the good words from many of you. So, thank you very much for having the patience despite the problems that have come. And questions. Let's see. Mm, people are typing questions. I don't see questions. Hello? Yeah, it's saying unable to connect to chat. Please try later. Do you have questions? Yeah, I'm on YouTube only. Right hand side there's live chat, है ना? Where I should go down or I should go up? मेरा को कुछ नहीं दिख रहा boss. Nice. Which is the last question you see? हाँ, below the end stream button there is it's a scroll down ना, काफी सारा उसमें scroll down हो रहा है. हाँ, नमस्ते तो दिख रहा है मुझको बहुत सारा. There is no questions. हाँ, okay, okay, okay. I do not see. I'm on the bottom only. Yeah. So please write your questions, everyone. If anyone has a question, please write down because I do not see questions, and I'll be very happy to answer. Baba, I can't see them. That's the problem. Unable to. Yeah, I'm scrolling. I'm scrolling. I'm scrolling. Ayushi Sharma, nice ma'am. बस उतना ही है. That's the last one. Ayushi Sharma. हाँ, that's the last one. Hmm. बस last. Very sad. Can you? I, no. No, it says the my last thing is unable to connect to chat. Please try again later. जबकि वो because on my YouTube का जो वो है ना उसमें तो लिखता है excellent condition connection, excellent connection है. Live chat में. Maybe you want to repeat the question to me. I can say something, some answers. It's sad. Maybe you want to give me a screenshot. Otherwise, we can have another session for question answers if you want. हाँ, screen में हाँ, yeah, give me a screenshot. I'm just waiting to see some questions, but I'm not able to see any question. That's the thing. I can suggest to collect all the questions, and I'm ready to have another session. Let me see. Yeah, tell me. You have sent me some questions.
Yeah, see the questions you can see.
Okay, let me see. So,
Hello.
yes, hello. Can you be a little bit further from the computer? Because then I'll be able to see the question. Like this. But then you don't shake it so much. So I have a question from Abhijit Dasgupta, who says that, if I've understood correctly, COVID-19 pandemic hampered the project. Of course it is, because it's delaying the all projects for the whole world. In fact, it's not only for the Hadron Collider. We are all at home like you, and we are trying to protect ourselves and our families and the communities. For that comes first, of course. And slowly, very very slowly, we will get back to work, which means that we will be able to take precautions, keep keep everything safe, and then we can get back to work. Another question is about string theory. Yeah, string theory, we have to wait to understand whether we have enough energies where we will be able to see some elements of string theory by experiment. That's the only way to observe and to then corroborate the theories. There are many many theories there. There are many talks as well, and many experts. I am working on an experiment. I am an experimental scientist, and there are many many experts at CERN who are specialized in string theory, and I would invite you to look at the very wonderful website of CERN, where there are loads of webcasts and answers about string theory. There are questions about antimatter, Daisy Kumar, but on the other hand, I think I explained antimatter a bit. Oh, can you summarize again? That is not easy for me. What are the other questions? Can you talk something? Can you please summarize? Wonderful. Thank you for your good words, everybody. I think it's not working because I'm unable to see why Nataraja statue in front of CERN. Okay, so the Nataraja statue was given to CERN as a gift from the government of India, in because because India has done wonderful work at CERN, and as a recognition, the Indian government had given the Nataraja statue to CERN. It was built in India, built in Chennai, in fact. Yeah. Okay. So other questions? Um, it's very hard about the questions. Higgs particle, Daisy Kumar, please take a look in on the CERN website. There are many beautiful, wonderful videos which are just being released these days because of the COVID-19 situation. So please Google up a bit and let's make the best use of the technologies that are at our disposal. Hmm? Anything else I can read? How can anyone join the mission? Just go to the CERN website. You will find a lot of answers, lot of possibilities, lot of work that can be done. Unfortunately, physical internships this year have been cancelled, completely cancelled, because of the COVID-19. Yeah. Okay. Is China building a bigger than CERN like experimental? Actually, it's a very good question, Katie. The point is that yes, they have plans. Yes, there are issues as well, because despite having the know-how, it's not simple to build something that is so big. It has to be a multi-country initiative. A lot of money is needed, and it's not easy to find the money. So governments have to understand where are the priorities, and I think I am not the best person to tell you which are the priorities at this moment. You can see the way our government is battling COVID-19 and the rest of the world as well. When will be your next lecture? So sweet. Thank you. I will definitely announce it. You can follow me on Twitter, and then I will announce the next lecture. Sheldon Cooper and his hypothesis. Okay, I will not take that question. Sorry. Sunita, 16-year-old student. May I contact you? See, I do get a lot of emails. Sometimes I have the time to reply, but usually I do. Please try. Otherwise, we can always connect. Not a problem. Please look at the public website of CERN. Google is great. There are a lot of answers. Look at the official website of CERN and you will have all official answers. Okay. Okay, Daisy. Then we come to Lal Chandra, who I have already answered. When will you next lecture? What books would you refer? Which books for what essentially? I mean, if you look for particle physics, there are lots of wonderful lectures, wonderful books. I think the first reference book that come up in Google are good. I personally studied Perkins and Martin, I think, if I remember well. But then that's for particle physics as such. And in particle physics itself, there are so many um, specializations. It's not easy for people to just say that I want to be a particle physicist and then he becomes how can I say, an expert in all the areas of particle physics. But this doesn't mean that it's not possible, because I do know a few people who are experts in every aspect, and that is incredible and so inspirational as well. Because there are people who's come from one field of let's say experimental physicist, then he becomes an accelerator physicist, then he creates some new ideas, and he has, I don't know, hundreds of patents. Then he creates a new experiment that is going into space, and these are the kind of people who are called noble materials. And I'm sure that within our community in India also, today there is no excuse. Everyone has access to knowledge, and I would only encourage you to go in this direction. I have been fortunate. I have had an exposure which I'm trying my best to learn as much as possible and sharing this learning. mm, Tao of physics. Yeah, well, let us not be too cynical about why it has been placed at CERN, Katie. There will always be conspiracy theories, and if we want to break our head, we can come with a conspiracy theory every day. The best is we should acknowledge and move on. We know exactly why. In India, it is very, very common. If you go from the length and breadth of India, you will see the Nataraj statue every single place of how can I say, learning, place of work. It's not something unusual. So giving a gift to CERN of the Nataraja should not be looked at with the lenses of a conspiracy theory. That's my take on it. Other questions? Sumit Triwari. Our ancient physics tech in India. Ancient physics tech in India. Well, I certainly believe that we have a very rich culture, very rich heritage. I would like to have the time to go into the greatest depth to study as much as I could in terms of relating the texts that we have in India to the scientific theory of today. There are certainly hints of of information, hints of knowledge, pearls of wisdom that are hidden in our culture. But it would take several PhDs together to document it in the best way possible. If I had a chance, another life probably, that's something which I would love to do. More questions? What about Gagan, madam? I am archaeologist. Does CERN? So sweet. Archaeologist. I have an idea that when the cavern was being dug at CERN to create those experiments or places for these experiments, a Roman villa was unearthed, complete with pots and coins and stuff. So, in India as well, there are some experiments of this kind. You might want to take a look and have a kind of a go at a research on the archaeological findings near heritage experiments, heritage buildings, because I know in Rome this is being done, which is why I mention it. But I will not digress more. So that's my answer. More questions are there? Is India building neutrino lab? Oh, I cannot answer immediately. I can just say that yes, there has been a fantastic effort in this direction. for an experiment called Indian Neutrino Observatory, INO. There has been an enormous amount of input in terms of students, PhDs that have been churned out, the postdocs that have been working there, technologies that have spun out. So I think it is worth a go to at least understand where we stand and how and what is the future of that experiment. Madam, what about environment due to accelerators? Not at all. It's Puneet Kumar. Is there any effect on the environment due to accelerators? There is actually zero effect due to environment, due to accelerators on the environment, simply because everything A happens underground, and B, beyond a meter of concrete, there is no radiation that can actually pass by. Okay, apart from neutrinos and things which are passing through the earth and they are going through your body all the time. So, in principle, the answer is no. Let's look at other questions. Um, Brief history of time. Of course, Stephen Hawking, so such a big scientist. I mean, I don't think I can comment much except that read the book, and it is indeed very illuminating. Other questions? Can you improve the focus a bit, Sri Prasad? I cannot see. Uh, I think we have exhausted the questions. How particle physics helps to describe the action of black holes. Certainly, I mean, this is one of the mysteries, and we are, as I explained also in the lecture about dark matter and dark energy and the formation of black holes, that has also the gravitational waves experiment that's going on, the LIGO experiment. All this is interconnected eventually, and I mean, this is going to be great for the next decades for science. And of course, if we find candidates of dark matter in the LHC or the HLLHC, which is the high luminosity LHC, and in the future experiments, this would be a very great triumph for science and for the experimenters as well. Okay, I think I've exhausted the questions here. What I can see on my phone. Anything else, Shri Prasad? Or
we can finish.
yes, okay. So I think I'm going to close then. Thank you. Okay, so thank you very much, everybody. It was pleasure to be here with you and to share some time with you. Thank you very much. Bye bye.